Okay, can we continue? Okay, so before we continue with the LCMV, I want to show you a short clip about the cocktail party effect. So cocktail party effect is actually when we are able, when there are many people around us, we're able to concentrate on a specific speaker. And with signal processing, it was challenging for a long time. Now it's possible to do some, there are significant progress in this area. So I want you to see some video clip.
What is the cocktail party effect?
It's this phenomenon where in the midst of a noisy cocktail party, any kind of noisy sporting event or newsroom, we're still able to focus in on the one conversation we want to hear and somehow tune out everything else.
And how can, now researchers, neuroscientists are very interested in this. Why is that? Why do they want to know where this ability comes from?
It's part of this whole phenomenon of selective attention, wherein the human brain can only really focus in intensely on one thing at a time. And this is a survival skill. You know, we're constantly bombarded by all this visual and auditory stimulation. We couldn't survive unless we could focus in like this, but we can also only really focus on one thing at a time. And that's what's at issue in distracted driving and all kinds of other limitations of multitasking.
Are there people who, is there like a small percentage of people who actually have sort of a super ability to focus on more than one thing, or is that a myth?
Yes, researchers at the University of Utah have found some of these people in the course of their other research. They think it's about 2% of the population. The real problem is that most of us think we can do that, and that can have some disastrous consequences.
Okay. Okay, so we want to move on to LCMV. So let's explain what is LCMV, and I will give you some motivation. And the motivation will come from what we talked about MVDR. So you can view that as an extension of the MVDR, minimum variance distortionless response. So suppose that we have an array of sensors like this. And suppose that we have desired source that comes from a certain direction. And we have undesired source that comes from another direction. And in addition, we have some other noise components. Maybe we have a few directional interferences. What we can do? Okay, so first what we can do is we worked with the MVDR. So the MVDR is defined as minimization of the variance of the noise at the output of the filter. Okay, so we find the filter for each frequency. Okay, so we always work for each frequency in this area. So for each frequency, we find the filter that minimizes the variance of the residual noise at the output of the filter, which is H transpose conjugate phi v H, subject to distortionless constraint, because we want that for each frequency we don't have any distortion of the desired signal, which means that when we estimate the desired signal, which is an estimate of x1f, we have two components. One is x filter desired plus v residual noise. So if we want that the filter desired will be equal to the original signal, this is the signal that is measured in the reference sensor, which is x1f plus v1f. If we want that X filter desired will be X1, so we don't have any distortion, we need the distortionless constraint, which we showed that it's similar to H transpose conjugate D equals to 1. This is the distortionless constraint. Because if we satisfy this, then we don't have distortion of the signal in the frequency F. Okay, so what do we do next? And then with MVDR, we can derive it, we showed it, and so on. So if for the distortionless constraint, see, we can find the solution, but with distortionless constraint, we use this propagation factor or steering vector for the desired signal. Now suppose that I know that I have undesired interference, and I know the propagation vector or steering vector of this interference signal. So I can use that as well, because here I try to minimize the amount of noise. But maybe I can now formulate a new problem like this. Let's minimize the total variance of the noise, okay? But before that, okay, I will write it like this. So you know that I can write the vector of measurements in the vector F, okay, for the frequency F, I can write it as X1F dF plus the noise vectors in all sensors. We saw that. And also we saw that we can separate this noise into two components. One component is the coherence noise, and the other component is the incoherence noise. So I can write it as X1F dF plus the noise, which is correlated with the noise in the reference sensor. I can write it as V1F multiplied with the coherence function, the partially normalized coherence function between V1 and V, just like we did here. This is the same. You see, this one equals to the coherence function, the partially normalized coherence function between X1 and X. So I can do the same for the noise. But then I have an additional component, which is the incoherent noise. Because generally, we don't have just noise source, one interference. We have additional sources, maybe the thermal noise, diffuse noise, so on. So I can add here the remaining part of the noise, which I will call it, let's call it V prime F. This part will be the part of the noise that is incoherent or uncorrelated with the noise in the reference sensor. This is something that we did, we showed in the formulation of the problem. Questions so far? Okay. So what I can do now, I can define a new problem. Suppose that I know this vector. For the MVDR, I didn't use this vector. Suppose that I know additional information. I know to estimate this vector. I know to separate the noise sources, the noise that are measured in the array, into two components. One component which is correlated with the noise in the reference sensors. The other components are uncorrelated. Suppose that I know to separate this. Does it help? Okay, so let's define now another problem to find an optimal filter, which will be like this. Okay, I will remove this because I want this space. You know, in our university, we have like larger than this, 3. So we can continue. We don't delete. Okay, so maybe next time, maybe we can have 2. So I don't need to delete, and I can keep some of the things. Anyway.
Like racks.
Okay, but even 2 like this also may be useful sometimes. Okay, but we manage with what we have. Okay, so I can define a new problem now. Let's define a new problem. Let's minimize the variance of the noise, okay, the total variance. Maybe even I will write it like this. Let's minimize this variance. Or, you know what? I will write it like this. Okay, so the total, because I don't want to confuse you, I want to keep that simple. So let's minimize the noise, just like we did for the MVDR. So I minimize the variance of the noise, of the residual noise at the output of the filter. Okay? But subject to 2 constraints. One constraint, subject to 2 constraints. One constraint is the distortionless response. Another constraint will be H transpose conjugate, F, complex conjugate of gamma, the steering vector of the coherent noise, will be 0. Because I assume I can estimate this vector. So I can formulate this problem. Can I solve this problem? Yes. Suppose that I know how to solve it. Actually, when I have 2 constraints, so I have Lagrange multipliers, 2 Lagrange multipliers for the 2, and I can solve this problem. So I can find a solution. So the solution to this problem is called LCMV, linearly constrained minimum variance. Because linearly constrained, so it's minimum variance. Minimum variance. So it's minimum variance, like the MVDR, minimum variance. But we have 2 linear constraints. So we have more than 1. So it's kind of extension of the MVDR. Any questions? So it's important first to understand the problem, the mathematics behind it. Now let's think beyond that. If you have questions, now is the time. If you don't understand, okay. So we see this formulation. So what did we do here? Did we do here? Suppose that we have like interference from a certain direction, and we know its direction, we know its relative transfer function estimate, its propagation vector. We know this. We can put a null towards this direction and suppress it completely. So when we have here the minimum variance, it will minimize the variance of this residual part. Okay? So I can write it in a more general way, which I will do soon. But first, I want to ask you a question. suppose that we compare the output SNR, narrowband output SNR, that is obtained, the output SNR that is obtained using the MVDR compared to the LCMV. With which method, which filter will we obtain higher output SNR? Okay, think. MVDR, what is MVDR? MVDR, we have signal subspace, and which contains signal subspace, signal plus noise subspace, and noise subspace. So in the signal plus noise subspace, we don't touch it. We keep it as is. In the noise subspace, we suppress all noise. We minimize. So we put to zero all that noise in the noise subspace. Okay? So we have in two different subspaces. One is distortionless, and we try to minimize. And then if we write the output SNR using this MVDR, it will be higher than the input SNR. So this will be equal to X1, and this one we try to minimize the variance of this one. Okay? Now with the LCMV, what we try to do, we add another constraint here, this one. So the interference that comes from this direction, because we know this, its propagation vector, it will not be measured in the residual noise. So it will be null. No contribution in this estimate. And then we try to minimize the variance of the residual noise under this constraint. So the signal subspace, we don't touch it. You see, signal subspace, we don't touch it. But within the noise subspace, we add additional constraint that the noise, the coherent noise, will be zero at the output, and we try to minimize its variance under that constraint. Okay? Now the question is, with which method will we be able to reduce more noise? MVDR or LCMV? Okay. Everybody says, almost everybody. I didn't hear MVDR. So this is actually intuitively, when people say an answer, when I ask this question, people will say LCMV. You know why? Why your answer is like this? Because what did you assume? You made an assumption. What was the assumption? That actually it's because I showed you all these examples, all the examples that we showed in the performance in this chapter are with that the directional noise is the most significant. We showed that the noise is composed of directional interference, which is significant, and very small amount, maybe 1% of thermal noise. So you say that if we put the directional noise, the coherent noise, we put it to zero, maybe it suppresses more noise, right? So even under these conditions, the MVDR suppresses more noise. Why? So this is a simple answer. But I knew that you may answer that LCMV, because this is the intuition. But I want, exactly. When when you compare the output SNR, so the output SNR is the variance of this, divided by the variance of the residual noise. So in both cases, the MVDR and LCMV, this part is the same. It's X1 because it's distortionless response. Both are distortionless response. So this part is the same. So the variance of X1, the X filter desired equals to the variance of X1, the same. The only difference is the variance of the residual noise. So here with the MVDR, I minimize the variance of the residual noise without any additional constraint. So necessarily, it will be lower when I add additional constraint. You know, in optimization, whenever you have additional constraints, the performance is lower because you have additional constraints. Okay, so first, from a mathematical point of view, the output SNR with the MVDR is higher than the output SNR with the LCMV. All agree? Or someone doesn't agree? We will explain until everybody agrees. Okay, so we have additional constraint. So this constraint, what do we achieve with this constraint? What do we achieve? We achieve that the coherent noise interference is 0 at the output of the filter. But the variance of the residual noise with this constraint, maybe it will not as good as the MVDR. Think about, suppose that we have noise like this, but this noise is very weak, very weak. And most of the noise comes from alternative, other types of noises. So if we, here with the MVDR, we don't care. We just care about the variance, the power. So we care about the power, the variance of the noise, and we minimize it. So we get the maximum amount of output SNR, the narrowband. So maximum noise reduction for this frequency. With the LCMV, we have the constraint that this contribution will be 0. So we can, even though it's very weak, we put that constraint, and then we are restricted how much noise we can reduce. And maybe the other noise is significant, is more significant than this part. Understood? Okay, any questions? Okay, if you don't have a question, I will ask a question. Okay? So we see, yes, somebody wants to ask. The noise, we can always split it into 2 components like that, always. Because one component is coherent with V1, the other component is the difference, the remaining. We always can do that. Even if we have combination of many types of noises, we can always do that. Because here we take each part of the noise, the part that is coherent with V1 and the part which is incoherent. We can always do that. Any other question? What is what? Okay, this is what I want. So you asked the question that I wanted to ask. So it's a very good question. You know, sometimes we say it's a very good question because we want to the next slide, or that is what I want to address. Exactly this question. The same question? Okay. What? So you tell me, if this is the same as this. What does it mean? It's on configuration of the array, but the array is the same for these two components. So you have an array. If D equals to this, what does it mean? It means that the sources, if they are both far-field, they come from the same direction. If they are near-field, they are in the same position. Because the steering vector, propagation factor, it depends on the correlation, including all the reflections. So if it's far-field, the desired source and the coherent noise come from the same direction. Okay? So obviously, if they come from the same direction, we are limited in there. We cannot reduce one by keeping the other. Okay? You see, these two constraints, if this equals to this, we cannot satisfy both. We can satisfy both if they are different. They come from different directions. Okay. So let's talk about the first question. The first question that you ask. So if the output SNR that is achieved with the MVDR is higher than the LCMV, what is the advantage of using LCMV? Why do we need LCMV? Under which circumstances? When there is advantage of using LCMV compared to MVDR? This is your question, right? Very good question. Let's think. What do you think? Let's think about the answer. Think about what or under which conditions it's better to use LCMV than MVDR. So this question, we can put it on the quiz. Actually, it's a very nice question. You see, I can tell you that people that work on array signal processing, I met people that work maybe sometimes a few years on array signal processing, and they don't understand this. If you ask them, they don't understand this difference between LCMV and MVDR. They think they know, but when you ask them, they say the wrong answer. They think LCMV, if it makes sense that it's better. But when something is better, you need to understand when is it better? Under which conditions? Okay. So when we compare something, we see that we compare the MVDR and LCMV, and if the objective is maximum output SNR, or equivalently, if the objective is to reduce noise, the power of noise, then always MVDR will be better. So LCMV is better when we talk about different objective. So the objective is not to reduce more power of the noise. Different objective. Okay, so what can be the objective? I'll give you an example. Sometimes, so if we talk about audio, but it's similar, I can give you many other examples. Not audio, I can give you underwater communication, radar. So I can give you a few examples. Let's start with audio. Do you agree that if I have non-stationary interference, even if it's weak, it's more disturbing than white noise, which is stationary? We know that when we listen to a signal, you can do it yourself. If you work on the speech enhancement example, assignments, if you worked on that, you could record yourself and you could add noise. So if you add white noise, white Gaussian noise or something like that, it's less disturbing. It's just we are tired when we try to listen to understand what somebody says, and there is like fan noise, air conditioner noise, some stationary car noise. even airplane noise. You see, sometimes you have a long flight on the airplane. There is the noise is stationary. And after maybe 10 hours, if you don't put earplugs, you feel headache. And you don't understand. Why do I have headache? Because you hear noise all the way, 10 hours. Noise, so you will have headache. You know? So people get used to stationary noise. They don't think it's disturbing so much. That's why they don't put earplugs. But it's not good for listening, and it makes the brain tired. And also, if you try to listen if you are in an environment, you try to listen, to see a movie or to a class, Zoom, and you have air conditioner noise. Or during the night, you put air conditioner and fan, and you have noise, so it affects the brain. That's why I recommend to put earplugs if you have such background, even stationary noise. But if I put some non-stationary noise in the background, you immediately feel, oh, it's disturbing. Okay? So suppose that here we have some directional noise or coherent noise, which is non-stationary. Like I put something like this. So if I continue the lecture like this, it's very disturbing. But the amount of energy of this signal is very low, right? Because the amount of energy is limited in the time, by time samples. So the amount of energy, something like this, is very low. So maybe this has very low energy. So if I use the MVDR, what does it try to do? To minimize the power of the noise, the variance of the residual noise. So it will find filter that minimizes this variance, the power of the residual noise. So it will try to minimize the amount of energy. If we have stationary noise, it will put more effort to minimize the more powerful noise, which is the stationary. Because this has very low energy, but it's very disturbing. So what do we need to do? Is to put here another constraint that even though this has low energy, we want to suppress the contribution of this noise source because it's very disturbing. Not because of the energy, because it's disturbing, for example, if it's non-stationary. Okay? So this is the advantage of using LCMV. So if we have weak signal, weak interference noise, that the significance of the interference, it's not because it's high power, but because it's disturbing more at the output based on some non-stationarity or other features that make it, at the output, make it more significant. So we want to give it more significance, more weight, so that we reduce that part at the output. How do we do that? We add a constraint on this interference. So when we add constraint on this interference, even though it's, in terms of power, it's weak. So we limit how much noise, the variance of the noise we can reduce. But we are willing to pay that. We're willing to sacrifice the variance of the residual noise because this part is important to us. So we added a constraint because we want to reduce this type of noise. Okay, and I can give you another example. Radar. Suppose that I try to detect the distance of a target. Where is the target, the range, direction, velocity, and so on. And suppose that I have an interference. And maybe the interference in terms of power is not strong, but it interferes with the signal that I send somehow, okay? Maybe they try deliberately, maybe they don't try, but because maybe they send another signal from another place and so on, or I have some interference, even weak interference from a certain direction, and I want to suppress that, even though it's a weak signal. So I can add a constraint to suppress source that comes from that direction in order to achieve a better signal that will enable me to find the range, direction of the target, and so on. And I can give you additional examples, but there is no need. Now you understand. Any questions? Okay. So now that you understand that, I suggest that once you meet somebody that works in array signal processing, try to ask him this question, see what the answer. Many people, they don't understand it somehow. I don't know why. Because sometimes it's confusing, or they're not familiar with the mathematics and the applications. But this is, and I can give additional examples, but that's enough for now. Maybe you can give other examples in your presentations, which you start today, right? Today at 5:30, you start your presentation. Okay. Now, after we discuss this, actually, this is what I wanted. This is the most important thing regarding the LCMV and the relation between LCMV and MVDR. Because after we define this mathematics and we understand it, that's it. You understand. All the mathematics is very simple because we add two constraints. So how do we do that? The mathematics behind it is very simple. So we define a matrix C. You see the column, the first column is the partially normalized coherence function between x1 and x. The second column is the partially normalized coherence between v1 and v. So if we define the constraint like this, it's the same as these two constraints. See, it's the same. So it's very useful to write the constraint such that we have constraint the matrix of the constraint, you see, C. So the matrix C actually contains coherence function or propagation vectors. So in this case, this matrix for each frequency is the size of m by 2. Sometimes we can add more constraints. That's why it's called linearly constrained minimum variance. So the constraint matrix is like this. So you see, the first one is actually the MVDR. If we have more constraints, we can add additional constraints. So we put 1 here for this part and 0 for the coherent noise. Now, to solve this problem, so we can define that the LCMV filter is the argument that minimizes the variance of the noise. Actually, here, instead of variance of the noise, I can put phi y instead of phi v. Do you agree or not? The same. Why is it the same? Subject to the constraint. So here, I can put phi y. Why is it true instead of phi v? Yes. So if we have the constraint of distortionless response, so actually phi y equals, you see, if I write it like this, okay, y equals to x, okay, plus noise. So if here this part will remain the same, we constrict it. So of course, when we have phi y, it equals to phi x plus the phi v x. Okay? But phi x, what is phi x? Okay, I'm going to remove this. We know that this part is x1f multiplied with df. Okay? So phi xf equals to phi x1f, which is a scalar, df dhf. Agree? So if we have over there H phi y H, okay, so it's this plus this. So what happens? So I can write it as H transpose conjugate multiplied with phi x, which is phi x1 H f df dhf hf. This part is multiplied with phi x plus h hf phi v f h. Agree? Okay? So I used phi y, summation of these two, and I used that. So I put that. Okay? What is this? Under the constraint of the MVDR, this equals to 1. So this is also 1. So when I try to minimize this, okay, so assuming, so we have, and the variance of the input is the same. This is independent of H, right? Because this is the input. This is the signal that is received in the single sensor. So it's not independent of H. So if I want to find H that minimizes this, is the same as finding H that minimizes this. Okay? Okay. That's why we wrote here H, phi y, which is the same. By the way, when we minimize the power, this is very nice to write it like this, because when we minimize the power of y, you know, so it's just like finding something like that. Sometimes in the literature we call it differently. Instead of MVDR, minimum variance distortionless response, which is defined here with phi v, we call this minimum power distortionless response. So we give it a different name. Sometimes people call both MVDR. But sometimes people call to this problem MPDR. So the question is, why to call it different names if it's the same? If you have two different names for the same thing, does it make sense? What? Exactly. Okay, so the answer is that if we estimate phi y or we estimate phi v, the results are different. If it's true, if it's the correct one, it's the same. MVDR and MPDR, they are the same. But if we estimate the correlation matrix of y or the correlation matrix of v, it's a different result. Okay? Good answer. So you listen. You understand. Okay? These small things are very important because it's relevant not only to this material, it's relevant to whatever you do. Understand the things. So we get different expressions, but the results will be different if we have estimates of these values, these matrices. So if we solve this problem, we can solve, we have this solution. So of course, if we can replace, instead of phi y, we can put phi v. We will get, in theory, it's the same LCMV, but instead of minimum variance, if I put here y, we can call it LCMP. Linearly constrained minimum power. In theory, it's the same. In practice, it's not the same. Okay? Let's continue. So now that you understand the most important things, we can skip some of the things. Okay? This, I talked about it. I talked that if we compare the LCMV, the noise reduction with LCMV is less than the noise reduction with MVDR. This is exactly what we talked. And we explained it. And of course, the noise reduction with MVDR is less than Wiener. Okay? And let's see an example. So we have the same example with the number of sensors is 5. And here we see the performances, the gain in SNR, the MST, the noise reduction, and the signal distortion with the LCMV when we have different parameter alpha, and alpha is the ratio. Okay, so alpha is the ratio between the variance of the thermal noise and the variance of the directional noise. Okay, and then we compare the amount of noise reduction. So what do you think? If I just want to compare the amount of noise reduction, so you know that the amount of noise reduction, when I add constraint, so I added this constraint, and then I try to minimize the noise. So what I said, that if the directional noise is very strong in terms of power, so the LCMV will suppress more noise because we try to eliminate this noise completely. So it makes sense. So the more that sigma u squared, that the variance of the directional noise, the more that this is more significant, if this is very significant, then the noise reduction will be higher using the LCMV. Okay? So if alpha goes up, it means that the variance of the directional noise is is smaller. So if alpha goes up, it means that this part is weak. So the ability of the LCMV to reduce noise is reduced because we try to eliminate something which is weak. So using the LCMV, so if alpha is large, it means that we try to put a constraint on a weak component. So it means that the noise reduction that we reduce with the LCMV is going down, and vice versa. But still, even though the noise reduction goes down, we are motivated to use the LCMV in case that this weak component is disturbing, not because it's strong, because it has some characteristics or some features that disturb us in the output of the filter. So if we see that, let's see that in this example. So here, the blue line is alpha equals to 0.1, 0.03. And then we have 0.1, the green, and 0.3, and then 1. So when we increase alpha, the noise reduction reduces. So we have less noise reduction. Less noise reduction, less output SNR. And of course, the distortion is 0. Why the distortion is 0? Because of this constraint. LCMV also, no distortion. Distortion is 0. But if the power of this is smaller, in terms of noise reduction, we have less noise reduction. But still, it might be better than the MVDR because we don't care only on the amount of noise reduction. We care about the characteristic. So sometimes low power noise makes a big difference. We don't want it at the output. And then we will use LCMV instead of MVDR. Okay, and then we can also extend it to additional constraint. So this is the constraint. So we can write it in this way. So you can have additional constraints. Sometimes we want, sometimes, for example, we add constraints based on some directions that maybe we don't have, we have interferences from certain directions, but we don't have them all the time. Sometimes we have from this direction, sometimes from this direction, sometimes from this direction. But we don't have detector for these interferences. So we put null to this direction and to other direction, even though we don't detect them. Because sometimes they appear, sometimes they disappear. Somebody tries to interfere with us. So once we measure the correlation, the steering vectors of these interferences, we can add more constraints to put to 0. Or maybe not 0, we can put some suppression to these directions. So the more constraints that we put, that we add, the less noise that we can reduce. The less noise in terms of power. But still, maybe this is something that we are desired to sacrifice. So we sacrifice the amount of noise reduction, but we want to suppress some directions which are interferences, even though there is not much power there. Sometimes they appear, sometimes they disappear, things like that. And we can solve this general formulation, you see, and this is the solution. So of course, if we have only the one constraint, the distortionless constraint, this is the MVDR. And here we have a list of what we learned so far. Wiener, maximum SNR, Wiener, MVDR, trade-off, LCMV. We see the relations between them. Very beautiful to see all these relations and their performances and how do they relate to each other. Any questions? Okay. So, so this part, I will talk, it will take more time. So I will talk about it tomorrow. So I will skip it for now, but I want you to understand, because generalized side lobe counselor, it's very important. And it's related, it's an implementation, a different implementation of the LCMV. So instead of a direct solution to the LCMV, what we showed here, this is a direct solution to the LCMV. So instead of finding a solution to this and implement it using like this, you see this is the inverse of the matrix and so on, of this phi y, we will implement it differently. But it's important, and we have 10 minutes, so I don't want to talk about it now. I will talk about tomorrow. I want to talk about something else, which 10 minutes will, I have 10 minutes, right? Or maybe finished, I don't know. Finished or 10 minutes? Maybe 5 minutes is okay? Okay. So I will talk about implementation in the STFT, okay? So for tomorrow, I want you to read the slides about the LCMV, you know, because I will give you a different way to have a solution which is relevant to implementation. And I want to talk about it. It will take me more time, so I want to talk about it in length tomorrow. For now, I want just to give you implementation with the STFT. So we talked about implementation in the STFT domain for single channel. So we also have implementation in the STFT domain for multi-channel. How do we do that? We take the short-time Fourier transform of the signals for each sensor, and then we work on each frequency bin separately. And then all the filters that we saw before, we just use them in the STFT domain. So it's very similar to what we did with single channel, when we do it with multi-channel. So we define for each frequency bin, we take the STFT, okay, this is the STFT. And then for each frequency, this is just the STFT implementation for each sensor. And then for each STFT, we write it like this. So instead of frequency, we have time frequency bin. And then we find a filter that is applied for each frequency bin, okay, along the time. So the filter will look like this. It's very easy. That's why I don't want to waste time on this. So we estimate each frequency, so each frequency bin, by applying the filter. And the filter is the same as just what we found in the frequency domain. So it's equivalent. So if you understand what we did with the single channel STFT domain compared to frequency domain, so it's the same what we do here. We find for each frequency bin a filter that is applied to the frequency bin in the STFT domain. Very similar. And then I can give you also an example with speech signal, just like we did with single channel. So if I show this example, that we have speech plus noise. So if we work with single channel, this is the result of speech enhancement with single channel. What you already did. You worked on that with a single channel. This is the single channel. If instead of single channel, I add more sensors, this is with 2 sensors, this is with 5 sensors. So you see, I improve the speech enhancement. I improve the output SNR. So you can take the code, the MATLAB code for these figures, for this example. You can play with it. Multi-channel speech enhancement with multiple sensors. So it's a very nice example. If you have time, go through, play with it, compared to the single channel. Okay? But there is not much to talk about it because it's very simple. It's just, instead of the Fourier transform, we work in the STFT domain. And we find for each frequency beam a filter. Okay? So tomorrow we'll talk about GSC, Generalized Side Lobe Counselor, and to see how it relates to LCMV, which is a topic by itself. We will talk about it. Okay, so I will assume that you understand LCMV, and we will show another way to derive the LCMV using GSC structure, which is very important because you find it a lot in the literature, both the MVDR and the LCMV and the GSC. Okay, any questions?